All right, welcome to this explainer. Today, we're going to cut right through the intense media hype and dive into the hard physics to understand the true potential and, frankly, the severe limitations of quantum radar. If you've been following defense tech lately, you've definitely seen some incredibly bold headlines floating around.
Let's start right off the bat with this seriously provocative claim. It has defense circles all over the globe buzzing. I mean, is it actually possible that a nearly invisible, state-of-the-art stealth plane can be spotted by just a handful of entangled photons? Well, today, we're going to look strictly at the source material, the verified physics, and the real-world engineering to figure that out.
Okay, here's our roadmap for today. We'll start with the quantum radar promise and quantum illumination fundamentals. Then, we'll get into defeating modern stealth technology, look at the global quantum arms race, explore the skeptic case regarding physics limitations, and finally, map out the roadmap to reality. Let's jump into Section 1, the quantum radar promise, seeing the invisible. This is the technology trigger that sparked this entire global race, the tantalizing promise of making stealth technology completely obsolete. The whole foundation of this hype basically boils down to this number, a theoretical 6 decibel signal-to-noise ratio advantage. Physicist Seth Lloyd first proposed this back in 2008, and the math showed an exponential improvement in detecting low reflectivity targets buried in bright thermal noise. To put that into perspective, achieving the same advantage with a classical radar would require pumping out 4 times the transmit energy. That is a massive promised leap in sensitivity, right? Moving to Section 2, Quantum Illumination Fundamentals. Let's talk about these telepathic twins. So how is that massive gain even theoretically possible? It all starts with a fascinating process called spontaneous parametric downconversion. By passing a pump laser through a nonlinear crystal, the system generates pairs of entangled photons. You can think of them as telepathic twins that share a deep, fundamental quantum connection. We call one the signal and the other the idler. The core mechanism relies on separating these twins. One photon, the signal, gets sent out via a microwave beam to probe the target area. Meanwhile, its twin, the idler, stays safely behind at the radar base, stored as a reference point. The radar then just waits to see if the signal photon bounces off a target and comes back home. But here is the absolute genius of quantum illumination. The environment out there is messy. As the signal travels, it suffers severe attenuation and interacts with the environment, which actually completely destroys the entanglement. However, and this is key, residual quantum correlations, known as quantum discord, actually persist. So when that weak signal returns, the receiver performs a joint measurement with the idler. It acts like a highly specific lock and key filter that isolates the true returning signal from ambient thermal noise, basically tossing out all the uncorrelated background photons. Section 3, defeating modern stealth technology. Essentially, leaving targets with no place to hide. So why is this physics so devastating to modern stealth aircraft? Well, classical stealth works by deflecting radio waves away using sharp geometry and by absorbing reflected RF power with very special coatings. They also rely heavily on electronic jamming to just overwhelm enemy receivers with artificial noise. But quantum illumination doesn't just measure raw returned power. It detects fundamental quantum correlations. That means traditional radar absorbent materials are theoretically totally useless here. Plus, if an aircraft tries to intercept and spoof the quantum radar, it would be instantly noticed because tampering with it inherently breaks the quantum state.
Which brings us to Section 4, the global quantum arms race. It's time to compare the lab results against the claims.
Because of this stealth-defeating potential, we are literally watching a global arms race unfold. But look at this stark contrast here between government announcements and verified academic tests. You have China's CETC claiming a 100-kilometer detection range in the open atmosphere back in 2016. But conversely, research out of the US, Canada, and the EU is hovering at technology readiness levels 3 to 4. These Western academic lab tests are operating over incredibly short distances in highly controlled environments.
Let's zoom in on those verified results for a second. In a landmark 2020 experiment by Berzanji and his colleagues, researchers did verify a quantum advantage. But they only proved a 1 decibel advantage over optimal classical illumination. And crucially, this was achieved at a fixed distance of just 1 meter. And they were generating these entangled microwave photons in a cryogenic environment cooled to 7 millikelvin. That is literally colder than deep space, right there inside the lab. This takes us to Section 5, the skeptic case. Let's talk about the very real physics limitations. This stark contrast between bold claims and modest lab realities brings us into what we might call the trough of disillusionment. There's deep skepticism in the physics community. Remember that incredible theoretical 6 decibel advantage we talked about earlier? Well, as engineers started trying to design these systems, they ran straight into a massive, unavoidable 10 to 11 decibel signal processing loss. This is due to something called peak to average power ratio, or PAPR. Why such a massive penalty? Well, classical radar uses carefully tailored constant amplitude pulses. You can control them perfectly. Quantum signals, on the other hand, are generated by spontaneous, uncontrollable quantum processes, like two-mode squeezed vacuum states. They're inherently wild, Gaussian random processes. And because you absolutely cannot optimize or tailor a quantum signal without completely destroying its quantum nature, it suffers from a terribly poor PAPR during pulse compression. In engineering, the net result is literally the only thing that matters. That 10 to 11 decibel PAP penalty completely swallows up the theoretical 6 decibel quantum gain. So when you actually do the math, it simply results in a net loss in overall radar performance once the signal is fully processed. As experts like MIT Lincoln Laboratories' Jeffrey Shapiro have pointed out, when you factor in this severe signal loss, a simpler, vastly cheaper classical noise radar is simply going to outperform a quantum one. Basically, if you take the low-powered signal of a quantum radar and try to amplify it up to military ranges, it effectively just degrades into a classical noise radar anyway. Finally, Section 6, the roadmap to reality. What are the actual engineering hurdles left to solve? For this tech to work outside of a highly controlled laboratory, engineers have to overcome some seriously towering hurdles. First, generating entangled photons at high power is incredibly difficult. Second, fixing that PAPR loss to overcome the inherent Gaussian randomness, that might literally be physically impossible. And operationally speaking, you'd have to figure out how to run highly delicate dilution refrigerators at millikelvin temperatures while they're bouncing around in the back of a military truck or sitting on a vibrating naval vessel. Add to that these severe swap constraints, that size, weight, and power. Plus, radars need to operate in the microwave band to penetrate the Earth's atmosphere. But entangled photons are way easier to generate in the optical band. The electro-optomechanical frequency conversion required to bridge that gap without destroying the fragile quantum state is staggeringly complex. Because of all this, practical operating ranges right now remain extremely, extremely short. So I'll leave you with this final thought to chew on. We've seen the incredible theoretical beauty of quantum illumination, but we've also seen the staggering engineering realities that are currently holding it back. If the strict laws of signal processing and classical physics continually win out over the quantum hype in practical applications, is this entire global race just a huge distraction? Or are we simply waiting for the next great unexpected breakthrough in quantum engineering? What do you think the true future of stealth detection actually looks like? Thanks for joining us for this explainer. We'll catch you next time.